Alright, so what we're going to do with this set of notes, I can't stress how important this idea of an integral as net change is. We started this discussion back in section 5.4 where we were looking at the integral as net change, or the displacement that we're looking at using the fundamental theorem of calculus. And so keeping this idea as the integral as net change, it's so important that we're going to do a second set of notes discussing this. And really in this set of notes we're going to do a lot of examples where we're looking at old free response problems and how they've incorporated this idea of the integral as net change. And you've seen several handouts that I said which were really good. The handouts, one where we started discussing how we were going to do the fundamental theorem of calculus and discovering the fundamental theorem of calculus, and then building up and working through several handouts that had to do with this integral as net change. All right, so just to remind you kind of where we were coming from in those handouts, if you had a car traveling at a constant velocity of 60 miles per hour in one direction, it's very easy for us to figure out how far the car has traveled. I went 60 miles per hour. In 2 hours, I've gone 120 miles. So the distance traveled, my distance traveled, or my accumulation, my net change in distance, because I was going at a positive velocity, is going to be my 60 miles per hour, my rate, times the time that I was covering that, which would give me 120 miles. But we've seen in our earlier discussion that if I were to take a look at a graph of the car's velocity, v of t over time, so I'm traveling at this constant 60 miles per hour, that if I'm looking at that, how does this answer manifest itself in the graph? That if we go for 2 hours, and if we were to calculate the area under the velocity curve, that area under the velocity curve is exactly the distance traveled. So our distance traveled, and then putting this back into our integrals, our net change in distance, net change in distance is always going to be equal to the area under the velocity curve. And in this case, area and definite integrals are going to be exactly the same thing because my velocity is positive. So in this case, the area, which is going to be the same as this definite integral from 0 to 2 of v of t dt. And then we learned fundamental theorem of calculus, which said that, hey, if we wanted to find that, then basically we would take, since we're doing 0 to 2 of a constant, 60 dt, that we would find the antiderivative, which would be 60t, and evaluate it from 0 to 2, which would give us 60 times 2 minus 60 times 0, and essentially this is 60 times 2 minus 0, are 60 times b minus a, another property that we've seen earlier in this. So the idea here is that our net change in position can be found by looking at the area under the velocity curve. Right? Now, suppose that we have a car and it travels along a straight road, and we give you this velocity function, t squared minus 4. V is measured in miles per hour, t is in hours. Sketch the velocity of the function over the interval. All right, so we're going from 0 to 5, and this is a parabola. So let's sketch our picture first, just so that we know what we're talking about. All right, so we're going 0 to 5, 2, 3, 4, 5. This is going to be my time. We're measuring our time in hours. This is going to be my velocity curve, which I'm measuring in miles per hour. We're using the formula, which is t squared minus 4, which is nothing more than a parabola that's been shifted down 4, has an intercept here at 2, If I want to, if I plugged in, let's put it over here so I can quit zooming up. T squared minus 4. If we want a couple of points in there, we know the vertex is at -4. So down 1, 2, 3, 4. If I were to put in 1, I'd get -3. If I were to put in 3, I'd get 5. If I were to put in 5, we'd get 21. All right, so we'll kind of assume that we have this all the way out. Our picture all the way up here to our 21. Okay, so what they're asking us to do is to evaluate 0 to 2, 2 to 5, 0 to 5, 2 to 0, plus 2 to 5, and then interpret what each of them means in context of the car. Okay, so let's start with the first one. So if I'm going the definite integral from 0 to 2 of v of t, which would be 0 to 2 of t squared minus 4 dt, whoops, and make sure you don't forget, even when I put it over here, that we put our dt in. That if I am going to integrate this, so this is just the arithmetic, the algebra of it, I'd have 1/3 t cubed minus 4t, and we would evaluate that from 0 to 2, which would give me 8/3 minus 8, and then minus basically 0. So I get 8/3 minus 24/3. 8 minus 24 would give me negative 16/3. And what would those units be? Those units would be miles. Oops. That would be in miles. Now, what does that mean in context of the car? This is saying that the car is traveling along a straight road, okay, but it has a negative velocity. It has a negative velocity. So we have to have a direction that we're going in. So let's say positive is forwards from a certain beginning point, and negative is backwards, okay? So at a certain point in time, for the first 2 hours, the car has traveled backwards. From their starting position a distance of 16/3 miles. 5 1/3 miles. So they went in this backwards direction for 5 1/3 miles. Okay. Then we take a look at 2 to 5. And we start to see that we can skip kind of the middle step and go straight to, now we're doing 1/3 t cubed minus 4t evaluated from 2 to 5. Now, the plug and chug of getting your answer, just go ahead and find it. All right, so through magic, plugging and chugging, put in your 5, put in your 2, subtract, your answer is 27. All right, and so once I get that, what does that tell me? That tells me for the hours from 2 to 5, so for those 3 hours from 2 to 5, the car has traveled forwards 27 miles. So from where they were at 2 hours, they've traveled 27 miles in the forwards direction. Okay. Now we're going to do 0 to 5. So I'm going to take the integral from 0 to 5, v of t dt, which again is going to be 1/3 t cubed minus 4t, evaluated from 0 to 5, which is going to give me that 125/3 minus 20 minus 0. All right. And this would be our calculation, so we would calculate what that is. All right, and we're going to get 21 2/3 miles. All right. So now let's think about this number and what it means. Let's come back up here. Now remember, this was our negative 5 1/3 miles. So we traveled in the backwards direction 5 1/3 miles. So from wherever we started, we went backwards 5 1/3 miles. Then from that point, we went forwards 27 miles. And then take a look at this number that we just came up with, our 21 2/3. How is 21 2/3 related to this 27 and negative 5 1/3? It's our net change. For the hours from 0 to 5, or for the first 5 hours, the car's displacement is 21 2/3 miles from his starting point in the forward direction, from his starting point. How did we get to that? Because he traveled 5 1/3 miles back and then 27 miles forward. So his net change in his distance, in his position, his net change in his position is going to be 21 2/3. All right. And then the last thing they have us going from 2 to 0. All right. So now I'm going 2 to 0, v of t dt, plus 2 to 5, v of t dt. Now let's think about what we're doing here. I don't need to do any more calculations. If I'm going 2 to 0, how is that related to 0 to 2? They are opposite of each other. So I'm basically taking back the distance that I have traveled. So 2 to 0 would be the opposite of negative 16/3 plus the 2 to 5 that we calculated, 27. So we're going to end up with 32 1/3. What does this number, 32 1/3 miles, represents? This would be your total distance traveled. So during the first 5 hours, the car traveled a total of 32 1/3 miles. Because what you're doing is you're taking the portion that was negative, going in the backwards direction, and you made the definite integral positive, so that way it was adding distance in. It was how much distance, not the distance with direction. We took out the direction and added a 27 to get our total distance traveled. So this one was our total distance. So hopefully this is all review of things that you should already know from our discussions earlier when we were doing the fundamental theorem in calculus. So when you are including and analyzing these comments and these definite integrals, you should always include units. Now, notice they gave you some additional information. Maybe I'll need to go back and adjust some things for that. They want to know, gave me this information. It's called read the problem. Started 4 miles away from a check part. So now I know where I started 4 miles away on the positive side initially. Okay, so now let's come back here and let's put this in terms of our checkpoint. So this one, since this is telling me that I traveled 5 1/3 miles back, so if I started 4 miles away from the checkpoint and I traveled 5 1/3 miles back in that direction, I am now going to be 1 1/3 miles behind the checkpoint. Okay, because I started 4 miles in front, and now I've gone 5 1/3 miles back, so I'm 1 1/3 miles behind the checkpoint. Okay, for 2 to 5, now let's think about where we are. At that point, that's where I am, 1 1/3 miles behind the checkpoint. I started at 4, I'm now currently at 1 1/3 behind it. Now I'm going to travel 27 miles forward. So if I travel 27 miles forward, where am I now? Where I am now always equals where I was plus my net change. So I've gained 27 miles, but I have to go with where I was, which was 1 1/3 miles behind the checkpoint. So I would end up at 25 2/3. So at this point, the car is currently 25 2/3 miles in front of the checklist, of the checkpoint. Because where I am is where I was plus my displacement. All right. Here, my net change 0 to 5, well, my net change was 21 2/3. Where was I? Let's think about it there. If I go from the beginning, this one I went from where I was at 2. This one I'm going from where I was at 0. At 0, I was 4 miles in front of the checkpoint. And my displacement is I've gone a total of 21 2/3 miles from that starting point. So at this point, hey, look, I am 25 2/3 miles in front of the checkpoint. So my current position is the same whether I went 2 to 5 or 0 to 5. 2 to 5 tells you your displacement 2 to 5. To figure out where I am, I have to take where I was at 2 plus my net change. So this 25 2/3 came from -1 1/3 plus the 27. This 25 2/3 comes from where I was at 0, which was 4 in front, plus my net change from 0 to 5, which was 21 2/3. Okay? And then your total distance traveled, again, was this idea of how much total did I travel. I traveled 5 1/3 miles backwards, 27 miles forward, so my car odometer changed 32 1/3 miles. All right? So it's just putting it all together, all of the things that we kind of need to memorize and understand about motion and change in quantity. Your displacement is your net change in position. You could also think of it as net change in whatever the quantity is. It's not always a position graph that you're looking at. You could have been looking at your change in amount of people. We saw that in the examples in the handout, that knowing how many people I have is a quantity function. My change in quantity of people is going to be my velocity function. Okay? And so displacement, net change in position, is your definite integral. Your total distance traveled, gross distance traveled, you have to look at your speed, but remember your speed is the absolute value of your velocity. This is, hey, you have to make all the areas positive. It's all the positive areas. So this equals your total area. Okay, total area. And again, I'm going to stress that's all positive. So whether it's above or below. Displacement is positives and negatives added in. You are moving forward if it's a positive velocity, moving backwards if it's a negative velocity. All right, and then your position at any time, S of B, is always found by where you were plus your net change in your position. Where you were plus your net change. So those are the key features that you're going to see in your AP problems, especially in the free response. All right, so now let's take a look at some examples here. We have our 2009 example. This was a calculator problem. We have Karen. She's riding her bicycle. She started at home at t equal to 0 minutes, and she arrived at school at t equal to 12 minutes. During the time on this interval, her velocity is modeled by this function. So this is our velocity function, our rate function. All right. So let's look at each of these parts and think very carefully about them. So for part A, I want to find the acceleration of her bicycle. Let's see, I've got room down there. I might be able to fit this one in right here. The acceleration of her bicycle at t equal to 7.5. So let's think about something. The acceleration at 7.5 is the derivative of the velocity at 7.5. So basically, to find this, I need the slope of v of t at 7.5. Okay? So here's my 7.5, which is right here. And slope, I can do, it's linear, so I can do change in y over change in x. I can take my point here, which is 7.3, and my point right here, which is 8.2, and I can calculate the slope of this line by doing change in y, 0.2 minus 0.3, over my change in x, 8 minus 7, 0.2 minus 0.3, negative 0.1 over 1, negative 0.1. Okay. Now, the nice thing about the AP is they will read your graph. So if there's work up here, they will take a look at it. So I can come down here and say equals negative 0.1, and I need to indicate units. So now let's think about this. So our velocity that we have, let's see, is miles per minute. So we have miles per minute. So this must be in minutes. And so now I'm taking the change in miles per minute, which would give me change in miles per minute squared. Miles per minute squared. All right, so using your graph, finding your acceleration. You also probably should answer the question. We'd like to have that in. So I would say the acceleration of Karen's bicycle at 7.5 minutes is negative 0.1 miles per minute squared. Now, we might also want to think about our sentence that we were saying when we had rates. You could also say here this idea that acceleration is your instantaneous rate of change in velocity. So you could say at 7.5 minutes, Karen's velocity is decreasing by 0.1 miles per minute squared. So we could write it out in that sentence that we had, the who, what, where, when sentence that we've been doing all along. All right. Now, let's look at part B. Using the correct units, explain the meaning of the definite integral from 0 to 12 of the absolute value of v of t dt in terms of Karen's trip. So as soon as I see that there's absolute value there, we know that that's looking at the not net change in her distance, but her total distance traveled. So the integral from 0 to 12, absolute value v of t dt, is the total distance traveled, during the trip. Okay? And then they want you to find a value for it. So thinking of our total distance traveled during the trip, that's where we actually take all of these areas and we add up all the positive areas. Now, the nice thing about the AP is they will read the chart. So if you come up here and you kind of do each of the areas, just to do your work up here, this area would equal 1/2 times 2 times the height of 0.2. So that's going to be 0.2. I'll come back and get them to answer the question, but maybe we can start filling in 0.2 plus. The nice thing is if you show it here, you don't have to show it here. We're just going to put it in. This right here has an area that is 1/2 of 2 times 0.2. So again, 0.2. So I would add 0.2. This has no area. Let's do, I'm going to go all the way to here because I can do this as a trapezoid. And so I'm just going to bring it down here. My area would be the two parallel bases, which would be 2 and 1, 2 plus 1 average, times the height, which is going to be 0.3. So that would give me 3/2 times, is this calculator? Oh, this is calculator. I don't know why I'm making this so hard. So this is 3/2 times 0.3. I'll just bring it down here, times 0.3. We're going to put it in our calculator to get an answer. Plus, all right now let's take this area. Okay, maybe I'll show this one up here. Area equals, the two parallel bases would be 0.2 plus 0.3 all over 2 times a height of 1. So 0.5 over 2 plus, oh, then we have a nice section, nice little rectangle. Area equals 1, 2, 3 by 0.2. So now we're going to have 3 times 0.2. And then our last area is going to be 1/2 1 times 0.2. Half of 0.2 is 0.1 plus 0.1. And then you would pick up your calculator and write an answer. All right, and from our calculator we get this is 1.8, and don't forget we need to have our units, 1.8 miles. You know, and when you have a calculator, when you're doing this, you should go ahead and, go ahead and calculate this and calculate this number and stuff as you go. It's just I didn't have a calculator handy to do that. All right, then let's take a look at the next one. Shortly after leaving home, Karen decides she left her calculus homework at home and she returns to get it. At what time does she turn around to come back home? So I'm going to come down here to start answering C. She turns around when her velocity is 0. So Karen turns around when v of t is equal to 0. V of t equals 0 when, and then we come up here and we take a look at our graph, v of t equals 0 here at 2. So she was going forwards, then she stopped, and then she's going backwards. She must be at home 4 to 5, and then continued back to her trip towards school. So this is going to school, going back to home. Here's where she's at home, and then this is going to school again. All right, so around when v of t equals 0, I guess we should say for the first time. So v of t equals 0 when t is equal to, we're at what, 2 minutes. At 2 minutes. All right, now let's take a look at D. Larry also rides his bicycle along the straight road in 12 minutes. His velocity is given by, a formula. They've already hit us with a graph. Now we're looking at a formula where W of t is in miles per minute for 0 to 12 minutes. Who lives closer to school, Karen or Larry? Now let's think about Karen very carefully first. Karen traveled a long distance, but her total distance, which we found up here, is not her distance from school, because she traveled towards school back home for a while and then started. So Karen's distance traveled, we need to pick where she starts from. That would be the entire trip. We don't want to worry about this, I went towards school for a while and then I went back home for a while. We really need to do the 5 to 12 for her. So her trip, distance traveled, is going to be the integral from 5 to 12 of v of t dt, and that will be her, how far she is from her home is from there. All right, and our Larry's distance traveled. All right, and we're going to look at this. We have this on a calculator. Before I put my bounds in, w of t dt, we should probably look at this and make sure that he didn't have any turnaround and go back as well, because we only want to know how far they are from school. So let's take a look at his and see what it is. So take a moment and let's graph this on your calculator. Just moving it down so I can see it. So I need to be y equals, let's clear out the ones that I had previously. All right, so we have pi over 15. I have to move up a little bit. Divided by 15, and then our sine of pi divided by 12. And t, and close our parentheses. All right, and we're doing 0 to 12, so our window, I'm going to go 0 to 12. And he's riding a bike, so he can't be going that fast. So let's do -6 to pi over 15. That's like 3 over 15, and this is only between 1 and -1. Let's go, let's not even do -6. Let's do -1 to 1, and let's see what happens. All right, so here's his picture coming across. This is a calculator problem. And as you can see, oh, look, it's positive the entire time. So keeping that in mind, then I know that I can go 0 to 12 for him, and that will be his distance traveled. So what we're going to do the 5 to 12 for her. So we're going to go grab our numbers that we had from up here, starting with this one, 3/2 times 0.3. Plus, let's see, what else do we have? We have this one, we have 4 of them that we have to add, so don't lose any of them. So this one was, actually I can just take it from the list right here. Once I know, I started with 3/2 times 0.3, the 0.5 over 2, plus the 3 times 0.2, plus the 0.1. Okay, so that will figure that out. Or you could just go, hey, it's the 1.8 minus the 0.4 that I traveled there. So that's going to be 1.4 miles. All right. And then Larry's distance traveled from 0 to 12. Oh, you're just going to get it off your calculator. We're just going to come over here. I have it in Y1. So I can come over here and do math, choose number 9. We're going to go 0 to 12. And we're going to put in our y1, so vars, yvars, function y1, and we're doing that with respect to x, and say calculator please tell me, and we get 1.6. So we get 1.6 miles for this one, and don't forget to answer the question. Karen lives closer to the school. And then we're done. And so that was a free response in 2008. Now I'm going to stop this video here. We have several more examples to do, but I think that's a good break. And then I may assign some for you to work on.